Hi everyone, in this video we're going to look at another way of representing square roots, cube roots, and higher roots in general in a notation that does not use the radical but rather uses the exponents, which makes more sense because these functions are paired with exponent functions like x squared and x cubed, etc. So here's the motivation. If I take the square root of a number x and then I square it, it's going to give me back x, right? For example, square root of 2 gives me back 2. Why is that? Well, because it becomes square root of 2 times square root of 2, which is square root of 2 times 2, which forms a pair, so it can be pulled out and you get 2, right? Now this means root x times root x is x. But when you have a number just x, then the exponent is 1. Now suppose we say that I can write root x as x to the power something, right? If that is true, then this can be written as x to the power something times x to the power something equals x to the 1. Or when you multiply numbers, or when you have the same base, the exponents add up, right? These add. So this is going to become the unknown plus unknown, but because they are the same thing, then 2 times this unknown must be 1, or this unknown must be 1/2. Right, so this is the motivation. Basically telling us that if I want to write radical x as an exponent, then the number in the exponent should be such that if it's added to itself, it gives me back 1, or it gives me 1. And the number that satisfies that is half, because half plus half is 1. Okay. So what is special about this number 2 is that it's a square root, right? That's why it's 1 over 2. If it's a cube root, it becomes 1 over 3. If it's a fourth root, it becomes 1 over 4, and so on. So for example, let's quickly just rewrite these as radicals. 1/2 means it's the square root of 64. We're not going to simplify it for this problem. 1/3 means it's the cube root. So this is cube root of negative 125. 1 over 5 means it's the fifth root. So as a radical, I use the same symbol, but right now that means square root. So I need to put a 5 in here to indicate in the radical notation that it is the fifth root. The other way around, we write with rational exponents. This would be 5xy. This is the fourth root. So since it's the fourth root, that is an exponent of 1/4. So now we start having rational exponents or fractional exponents, which makes things better because it's more consistent with our notations. This here is a cubed p over 2, and it's all raised to power 1 over 5 because it is the fifth root. So if you have the nth root, the power is going to be 1 over n when written as an exponent. Now, the regular exponents have these properties, which is, like x squared times x cubed is x to the 5 because the powers add up. We have similar properties for rational exponents. If you have the same base, okay, so if you have the same base b, then when you multiply two numbers with the same base but different exponents, the exponents add up. And the same thing with same base division. In this case, the powers subtract. If you have an exponent of an exponent, then they multiply. If you have two numbers inside to the same exponent, you can split it to write a to the n times b to the n. And similarly, if you have a fraction raised to power n, it can be split as a to the n over b to the n. And using these properties, we can simplify some terms or expressions so that they don't look as messy as they would without simplification. Let's look at some examples. Let me move that a little bit here. So the first one says 6 to the power 1 7 times 6 to the power 4 7. Now that's the same base, right? Which means I can just add them up. 1 over 7 plus 4 over 7, which is 5 over 7. Right? So this product can be written as a single term. The second one here, oh, I see why I gave it more space. First, let's deal with the numbers. 32 over 16 is 2. So it's 2 times x to the 1/2 over x to the 3/2. Now here, the base is x. Yeah, so same base, which is x. So this comes out to x to the 1/2 minus 3/4 because it's a division. So it's 2x. Now when you subtract 1/2 and 3/4, you make the common denominator 4. And this is 2 minus 3. So this is 2 times x to the negative 1/4. Okay, so this entire fraction simplifies to become 2 times x to the negative 1/4. More examples. Use rational exponents to simplify these. So let's go one at a time. First of all, it's a cube root, so I write this as to the power 1/3. Next, I rewrite 27 as 3 cubed a to the 15 to the 1/3. Now I use this property here, right? If I have a power n on the outside, I can split it. So this becomes 3 cubed to the 1/3 times a to the 15 to the 1/3. Now I use this property, say that if I have an exponent of an exponent, the exponents multiply. So this is 3 to the power 3 times 1/3 a to the power 15 times 1/3. 3 times 1/3 is 1. 15 times 1/3 is 5. So this is 3a to the power 5. We do the same thing in the next problem. X to the 6 y squared 1/4 becomes x to the 6 to the 1/4 y squared to the 1/4 x to the 6 over 4 y to the 2 over 4 x to the 3 over 2 and y to the 1/2. So we can stop there. Second one. Now this one you have to be careful. There are two radicals here, right? So the first radical, that's a 1/3. And the second radical is a 1/2. So what you have is x to the 1/2, right? That's root x. And this entire thing is to the 1/3 because it's the cube root of square root of x. And then using the property of multiplication, it's 1/2 times 1/3, which comes out to be 1/6. The next one. Now here, this is different from the previous one because there's a multiplication, right? This is 1/2 times 1/3. So in this case, the exponents are going to be added and not multiplied. So you end up with a different answer than the previous one, right? These are different. Because they are two different things. Here you're multiplying the square root with a cube root. Here you're taking the cube root of a square root. Okay, so now when you have these rational exponents, what you notice here is that if these are written nicely, you know, like for example 27 is not written that nicely, but if I write it as 3 to the 3, then these rational exponents kind of work really well, because some things may cancel out, some things factor out. So that tells us that it's usually easy to simplify the radicals by factoring. So for example here, 75, now 75 is not even, it's divisible by 5. It gives me 15, 5, 3, 3, 1. So it is 5 squared times 3 to the 1 half, which becomes 5 squared to the 1 half times 3 to the 1 half, which becomes 5 to the 2 times 1 half, 3 times 3 to the 1 half. Now 2 times 1 half is 1. So this is 5 times 3 to the 1 half. Similarly here, 54 is 3 cubed times 2 to the 1/3, which becomes 3 cubed to the 1/3 times 2 to the 1/3, which becomes 3 to the 3 times 1/3 times 2 to the 1/3, which becomes 3 times 2 to the 1/3. 64, that is 2 to the power 2, 4, 8, 16, 32, 64 is 6 to the power 1/5. So these just multiply straight up. 6 times 1/5 to give me 6/5. 500, that's 5 times 100. So it's 5 times 10 squared times xy squared to the 1 half. And in this case, there's more than 2 terms, but it's the same property. So you can distribute it to each of them. 5 to the 1 half, 10 squared to the 1 half, x to the 1 half, and y squared to the 1 half. That's 5 to the 1 half, 10 to the 2 times 1 half, x to the 1 half, y to the 2 times 1 half, which is 5 to the 1 half times 10, x to the 1 half times y, or 10y 5x to the 1 half. Now how you represent the final formulation depends on you. If you want to use radicals, you can use radicals. But the important goal is to understand that writing these radicals as rational exponents help us simplify things a little easier, because then they follow the properties of exponents. That's it for this video. In the next videos, we are going to apply all of this knowledge for, we'll move on to more complicated expressions and not just numbers, and we will see that the same rules and the same working theory applies for those as well. That's it for this video. Thank you.